After a detailed discussion on Dirac equation, now today we are going to see the solution of the Dirac equation for a free particle. I hope you have the Dirac equation for a free particle in your mind because you have studied it in the previous lectures. Actually, in this lecture, we will see the plane wave solution of Dirac equation. Okay, this plane wave solution, it is also called free particle solution because we will start with the Dirac equation for a free particle and try to solve this equation in the form of a plane wave. So let us see what you have learned in the previous lecture. You have actually studied that Dirac equation for a free particle is given like this. This is C times alpha dot p plus beta mc square operated on psi. This is equal to E psi. Can you remember it? This is the famous Dirac equation for a free particle. Now, this alpha dot p, alpha is actually a three-dimensional vector operator and p is the momentum operator, or you can say momentum matrix. And this is simply equal to alpha x px plus alpha y py and plus alpha z pz, Okay. So when we will substitute this expression alpha x px plus alpha y py plus alpha z pz instead of this alpha dot p, our equation will become like this. This is C alpha x px plus C alpha y py plus C alpha z pz plus beta mc square psi equal to E psi. Okay. This is a Dirac equation for a free particle and you have already learned about this equation in your previous classes. Okay. Now, in fact, to get the plane wave solution of this Dirac equation for a free particle, first of all, we will cast this equation into a simpler form, or you can say into a more explicit form in terms of the matrices associated with the operators alpha and beta. Okay, so when we will use the specific matrices for the operators alpha and beta and this wave function or the eigenfunction psi, when it will be expressed as a 4-element column matrix or 4-component column matrix, then what will be the form of this equation 1b, you can see. Okay, you have learned in the previous lecture that actually in the 4-dimensional space, this psi has 4 components, and that 4 components you can express in as a column matrix. So instead of this psi, we write simply a column matrix psi 1, psi 2, psi 3 and psi 4. Okay, psi 4. So what we will do? We will simply use the specific matrices for the 3 alphas, that is alpha x, alpha y, alpha z, and 3 and beta. Okay, and psi will be replaced by this 4-component or 4-element column matrices. After doing this, you will get this particular result. You can see this matrix will be in this form: mc square 0 cpz cpx minus ipy. Okay, this is just a 4x4 matrix. 0 mc square cpx plus ipy minus cpz cpz cpx minus ipy minus mc square 0 and cpx plus ipy minus cpz 0 minus mc square. Okay, and this matrix is operated on the column matrix psi 1, psi 2, psi 3 and psi 4, and then your result is E psi. So E, and instead of psi we will again write this column matrix psi 1, psi 2, psi 3, psi 4. Okay. Now you can see this matrix equation can be written just in the form of 4 simultaneous linear equations. You can see just this is a very simple expression. You can see this mc square will be operated on this psi 1, and so the first term will be mc square psi 1 plus 0 operated on this psi 2. So that will be simply 0. So I have not written here 0 psi 2. Okay. And cpz operated on psi 3. So this is cpz psi 3. You can see. And the fourth element, this is cpx minus ipy, will be operated on psi 4. And that is cpx minus ipy psi 4. And that will be equal to E operated on this psi 1. So this is equal to E psi 1. Okay. Similarly, this 0 operated on psi 1, that will be 0 psi 1, that is 0. So I have not written in the second equation 0 psi 1. But mc square operated on psi 2, you can see this is mc square psi 2. Again, cpx plus ipy operated on psi 3. So this is cpx plus ipy psi 3. And minus cpz operated on this psi 4. So this is minus cpz psi 4 and E psi 2. Okay. This is equal to E psi 2. And in this manner, you can take the multiplication or the operation of this transformation matrix on this column matrix, and then the remaining 2 equations you will get. I am not repeating the terms. You can easily see it. Okay. So this matrix equation, you can see, has been transformed into the 4 simultaneous equation, which I have mentioned it here. Okay. Now this 4 simultaneous equation can be written in more convenient form by taking simply the terms in the LHS into RHS. So when you will bring the terms in LHS into RHS, what will be your result? You can see this, all the terms in the LHS will get changed in sign. So the first term will be E minus mc square psi 1. Okay. Minus cpz psi 3 minus cpx minus ipy psi 4, and that will be equal to 0. So you can see I have written it here. This is E minus mc square psi 1. The page has been turned, but this will be just okay. Don't worry. This is just a drawback of my device because it is now old. And similarly, you can see when we will take this 3 terms in LHS in second equation, then this will be again E minus mc square psi 2, and this second term will become minus, this third term will become plus, sign will be just reversed. Okay. So the second equation becomes E minus mc square psi 2 minus cpx plus ipy psi 3 plus cpz psi 4 equal to 0. Okay. And in the similar manner, the remaining 2 equations can be written like this. This is E plus mc square psi 3 minus cpz psi 1 minus cpx minus ipy psi 2 equal to 0. And the fourth one is E plus mc square psi 4 minus cpx plus ipy psi 1 plus cpz psi 2 equal to 0. Okay. I is actually iota. And you know that in this equations, the operator, this px is defined by minus I h bar del x. This is just x momentum operator. And instead of this del x, you may equivalently write simply del x. It means del x is just equivalent to del x. This is just a manner of writing. okay, partial derivative. And this py is equal to minus I h bar del del y, which can be written like this, minus I h bar del y, and pz is minus I h bar del del z, which is equivalent to writing minus I h bar del z. And actually in this equation, this psi, as you have learned, this is just a 4-component column matrix, okay. And the Dirac equation, in this case you can see that this is just a set of 4 first order linear partial differential equation, okay. Now, as I have told you that in this lecture our aim is to find the plane wave solution of this very equation. So our aim is now to solve these 4 equations defined in equation 2, and the solution should be in the form of a plane wave. So the plane wave solution, you know, this is in the form of e to the power I k dot r minus omega t. This is called plane wave. And so the 4 components of the wave function psi can be written as psi k of rt equal to uk e to the power I k dot r minus omega t. Actually, this exponential factor represents the plane wave, and these uk are actually the 4 numbers. uk are actually the 4 numbers, okay. In fact, this subscript k means 1, 2, 3, 4. So this equation 3 represents actually the 4 equations, okay. And the 4 equations will be psi 1 of rt equal to u1 times e to the power I k dot r minus omega t. Similarly, you can define psi 2, psi 3, psi 4, okay. And correspondingly, this uk will be u1, u2, u3, u4. And remember, these all u's are actually numbers, okay. In fact, this psi k of rt is what? Actually, these are eigenfunctions of the energy and momentum operators. And the eigenvalues of the energy operator is E equal to h bar omega, and that of the momentum operator, the eigenvalues are h bar k, okay. You know, momentum is equal to h bar k. These are the eigenvalues of the energy operator and the momentum operator. And these 4 psi are actually the eigenfunctions of the energy and momentum operators, okay. Now, when you will substitute this equation 3, or you can say that when we will use this equation 3 in this equation number 2. So instead of this psi 1, what we will now write? Instead of psi 1, now it will be written that this is u1 e to the power I k dot r minus omega t, okay. And instead of this psi 3, what you will write? At the place of psi 3, now it is written that this is u3 e to the power I k dot r minus omega t. This will be written, okay. Similarly, at the place of psi 4, we will write u4 e to the power I k dot r minus omega t, and that will be equal to 0. Now you can see, when we will replace psi 1, psi 3 and psi 4 in this first equation by the corresponding plane wave solution, this plane wave factor, that is e to the power I k dot r minus omega t, will be just a common factor. It will be present in all the 3 terms in LHS. So that can be taken as a common factor, and when you will divide the 0 in RHS by this factor e to the power I k dot r minus omega t, the result will be 0. So simply, what will be our result? Actually, the equations in 2 then become simply at the place of psi 1, psi 2, psi 3 and psi 4, there will be u1, u2, u3 and u4. So you can easily write these equations in equation number 2 in terms of u1, u2, u3 and u4. The result will be what? Simply at the place of psi 1 there will be u1, at the place of psi 2 there will be u2, at the place of psi 3 there will be u3, and at the place of psi 4 there will be simply u4. So replacing psi 1, psi 2, psi 3, psi 4 by u1, u2, u3, u4 in equation 2, our equation will now become like this. You can see. This is E minus mc square u1. Actually, I have also, yes, only you have to replace. You can see. See this. So, in every equation, psi 1, psi 2, psi 3 and psi 4 has been replaced by u1, u2, u3, u4. And so, the four equations in equation number 2 now becomes like this. This is E minus mc square u1 minus cpz u3 minus cpx minus ipy u4 equal to 0. The second equation is E minus mc square u2 minus cpx plus ipy u3 plus cpz u4 equal to 0. The third one is E plus mc square u3 minus cpz u1 minus cpx ipy u2 equal to 0. And the fourth and last equation is E plus mc square u4 minus cpx plus ipy u1 plus cpz u2 equal to 0. Okay. So now you can see that in these equations u1, u2, u3 and u4 are numbers. So these are actually the four homogeneous equations, and you know from the theory of determinant that these equations will have non-zero solution, or you can say non-trivial solution, only when the determinant of the coefficients of u1, u2, u3, u4 will be equal to 0, will vanish. So only then you can say that these equations will have non-trivial or non-zero solution. So to get the non-zero or non-trivial solution of equations in 4, we will simply equate the determinant of the coefficients of u1, u2, u3 and u4 in this equation 4 equal to 0. So let us see. What are the coefficients of u1, u2, u3 and u4 in equation 4a? The coefficient of u1 you can see is E minus mc square. And in this first equation, u2 is not present. But if your aim is to write u2 2, you can write 0 times u2. Okay. So the coefficient of u2 in this first equation a is 0. The coefficient of u3 is minus cpz. Coefficient of u4 is minus cpx minus ipy. Okay. So in the first row of this determinant, we will write this. This is E minus mc square. This is coefficient of u1. And this 0 is coefficient of u2. Minus cpz is the coefficient of u3. And minus cpx minus ipy, this is coefficient of u4. Similarly, from the remaining three equations, you can see in the second equation, the coefficient of u1 is 0. And that of u2 is E minus mc square. The coefficient of u3 in that equation is minus cpx plus ipy, and that of u4 is cpz. Okay. In the third equation, you can see that the coefficient of u1 is minus cpz, and that of u2 is minus cpx minus ipy, and that of u3 it is E plus mc square, and u4 is not present in the third equation. So the coefficient of u4 we will write 0. Okay. And in the similar manner, you can see the fourth equation, that is equation number 4D, where you will find that the coefficient of u1 is minus c times px plus ipy, coefficient of u2 is cpz, and that of u3 is 0, and the coefficient of u4 is e plus mc square. So this determinant must be 0 for getting the non-trivial solution of those four homogeneous equations. It is obvious from the theory of determinant. Okay. I hope you have a concrete knowledge of determinant. You have definitely studied determinant in detail in your course on mathematics. So you can see this determinant, which I have defined in this equation 4, that this is simply a determinant of rank 2. Okay. So solving, when we will solve this determinant which is of rank 2, you will get, I have not done the algebra here, this is just a homework for you. You can solve this determinant, and then you will find that after solving this, our result is e square minus m square c4 minus p square c square times e square minus m square c4 minus p square c square equal to 0. Actually here, when you write this p square, that means what? This p square is actually equal to px square plus py square plus pz square. Okay. I have not done the algebra, but you can do it. Okay. In fact, this is just a determinant of rank 2. So here there is two factors, and although both factors are equal here, so you can say that if this product is 0, each and every factor will be separately equal to 0. Since here both factors are same, so there will be only one solution, that will be e square minus m square c4 minus p square c square equal to 0. And so from here you can see, if we find the value of e square, that will be in fact p square c square plus m square c4, and so e will be equal to plus minus a square root of p square c square plus m square c4. Okay. Actually, this result actually shows that that this result is actually in accordance with the Schrodinger picture. Okay. And hence we can assign the numerical values of 2 of u's, and the remaining u's can be calculated then. Actually, this is a 2 by 2 determinant. Sorry, this is a determinant of rank 2. So for its solution, we will put the values of any two numbers u1, u2, u3, u4. Out of these 4, we will assign the values of any two arbitrarily, and then we will find the values of other. Okay. And as you can see that this equation has actually two roots, both positive and negative. So we will take both of the roots to get the solution. So let us first of all see its positive root. Its positive root has been denoted by the symbol e plus. This plus sign in the subscript only represents that we are talking about the positive root of the square root. Okay. So e plus, now we define it like plus a square root of p square c square plus m square c4. Okay. So in fact, as I have told you that in this condition there will be two linearly independent solutions, and those two linearly independent solutions can be written in a convenient manner by taking the value of u1 equal to 1 and u2 equal to 0. You have to set these values yourself. Okay. So remember, you have to put u1 equal to 1 and u2 equal to 0. Once you put the value of u1 equal to 1 and u2 equal to 0, then you can see the remaining u3 and u4 can be found from which equation? From which equation you can find? Let us see here. As u1 is equal to 1, u2 is equal to 0, these are known, and our aim is to find u3 equal to what and u4 equal to what. So in these four equations you have to select the two equations from which we can find u3 and u4 when u1 and u2 are known. Okay, when you will see the equation number 4a, here u2 is not present in this equation. Okay, only u1 is present. So substituting the value of u1 only, we cannot find the value of this u3 or u4. In fact, when you will see the equation number c, that is 4c, see here. Here u1 is present, which we have taken 1. u2 is present, which we have taken 0. So from this equation 4c, we can easily find the value of u3. So what we will do? At the place of u1, now we will write 1. At the place of u2, we will write 0. So this equation 4c will become what? This will be simply e plus mc square u3 minus cpz, and this third term will become 0, and that will be 0. Okay, so cpz u1 will be equal to e plus mc square u3. Are you getting the things or not? When you will substitute this value, you can see what will be the value of u3. I am putting it just here. You can see that in that equation there is e plus mc square into u3, and there is minus, what is the second term? You can see there is minus cpz u1 and this much u2. u2 is 0, so third term will be 0. Again the page has been turned. Let us see. Okay, sorry. This will be just okay. The device is hanging. Okay. Now see, this will be e plus mc square u3 minus cpz u1, but we have taken u1 equal to 1, and this third term will be 0. So what will be our result? We can see this is minus cpz u1, and u1 is 1, and the third term we have seen that this is equal to 0. So you can see, and u1 we have taken 1, so this e plus mc square times u3 is equal to what? This is cpz, and from here when we will find the value of u3, you can see this will be cpz over e plus mc square. Okay, so you can see I have written here that in this condition u3 will be equal to cpz over e plus mc square. Now you can see the 4d equation. See here, in this equation u1 and u2 are present. u1 is 1 and u2 is again 0, so this last term will vanish and u1 will be 1. So from here you can easily find the value of u4. u4 will be simply equal to what? This will be c px plus ipy divided by e plus mc square. Okay, e plus mc square. So you can see I have written it here that this u4 is equal to c times px plus ipy divided by e plus mc square. Okay. So u3 and u4 has been obtained by selecting the value u1 equal to 1 and u2 equal to 0. Okay. Now see. Now take the another set of u1 and u2. Now u1 is taken 0 and u2 is taken 1. So again from those two equations you will get in this condition u3 will be equal to this much. I am not turning the page, but because you can find it out easily. And u4 will be then equal to this much, minus cpz over e plus mc square. Okay. Now when one consider the negative square root, then we will write the value of energy E minus equal to minus root over c square p square plus m square c4. Okay. This E minus is just a symbol to represent the negative square root of the value of energy. Okay. Now again to find the solution, or you can say to obtain the two new solution from the equations in 4, we will now substitute u3 equal to 1 and u4 equal to 0 arbitrarily. When you will put the value of u3 equal to 1 and u4 equal to 0, you can find the value of u1 and u2. And for this, you have to use the equation defined in equation 4a and 4b. You can see here we have defined u3 equal to 1 and u4 equal to 0. Okay. So in that condition, from this equation A, you can obtain the value of u1. Okay. And from equation B, when you put the value of u3 and u4, you can obtain the value of u2. So from these two equations, 4a and 4b, substituting the values of u3 and u4 arbitrarily equal to 0 and 1, we can obtain the two new independent solutions of this equation. And what are those solutions? You can see. In the first set of u3 and u4, we have considered u3 equal to 1 and u4 equal to 0. Then from equation A and B, we obtain u1 equal to this much, cpx minus ipy over E minus mc square, and u2 is equal to minus cpz over E minus mc square. Now we will now take the another set, that is u3 will be now taken 0 and u4 will be taken 1. And then again you can see u3 equal to 1 and u4 equal to 0. Then again from those two equations you will get u1 equal to this much, u1 equal to cpz over E minus mc square, and u2 will be c times px minus ipy minus divided by E minus mc square. You can do it. Okay. I have not turned the page to show that the result for u1 and u2 will be like this, but that is a very simple algebra. You can do it. Okay. Now, all these four solutions can be normalized. You know, when you want to normalize an eigenfunction, you have to multiply it by a normalization factor. Okay. So let us consider that n is the normalization factor. Okay. So in this condition, when we will substitute the values of u1, u2, u3 and u4, we will simply multiply that values by this normalization factor n. Okay. Now you know the condition for normalization is the scalar product of psi with psi is equal to what? This is psi star psi, and that is equal to 1. This is the normalization condition. Now, as you know that this psi has actually the four components, psi 1, psi 2 and psi 3, psi 1, psi 2, psi 3 and psi 4. And Corresponding to those four components, the numbers u has also four values, and those are u1, u2, u3 and u4. And we have seen that the normalization in the plane wave solution, when we will take the product, let us see, when you will take the product of psi1 star times psi2 times psi1, what will be that? Psi1 star, this will be u1 e to the power minus I. When you will take the complex conjugate, then the power on e will be minus I k dot r minus omega t. Okay, sorry, here there will be a star. Okay, and plus into psi1. Psi1 will be u1 into e to the power I k dot r minus omega t. Minus omega. So what you are seeing? E to the power minus I k dot r minus omega t and e to the power I k dot r minus omega t. When these two exponential factors will get multiplied, the result will be e to the power 0. So this product is simply equal to u1 star times u1. u1 star times u1. Okay. So you can, for simplicity, I am writing it here. You can see that this is psi1 star psi1 plus psi2 star psi2 plus psi3 star psi3 and plus psi4 star psi4, and that will be equal to 1. But as you can see, when we take the product psi1 star times psi1, then that becomes simply equal to u1 star u1. In the similar manner, you can say that psi2 star times psi2 will be simply equal to u2 star times u1, psi3 star psi3 will be u3 star times u3, and psi4 star psi4, that will be simply equal to u4 star u4. Okay. So I have written it like this: u1 star u1 plus u2 star u2 plus u3 star u3 plus u4 star u4 equal to 1. But as we have considered that n is the normalization factor, so when we will substitute the values of these numbers, you have to multiply each and every u1, u2, u3, u4 by n. So the value of u1 star, you know that u1 is equal to, in fact, 1. u1 is equal to 1. In fact, I have taken here the first set of solution. This solution I am just going to take this solution. Remember, there are 4 solutions. In the similar manner, we can obtain all the in all cases the normalization factor. But to get the normalization factor, I have considered this solution. So in this case, u1 is equal to 1, u2 is equal to 0, u3 is equal to this much cpz over e plus mc square, and u4 is equal to this much. Among these 4 values, you can see u1, u2, u3 all are actually real, and so their complex conjugate will remain same. So u1 star will be also 1, u2 star will be also 0, u3 star will be also cpz by e plus mc square. But the complex conjugate of this u4 will be what? That will be c px minus ipy. Mark it. u4 is c times px plus ipy over e plus mc square, and when we will take its conjugate, then that will be c times px minus ipy, okay, and divided by e plus mc square. Okay. And multiplying by the normalization factor n to each and every term, then you will see this will be n into 1, n into 1. So n square will be in each term as a common factor, where n is the normalization factor. So n square has been taken as a common factor. Now, the first term will be 1, second u2 has been taken 0. In this condition, you can see u3 was also real, and that was cpz by e plus mc square. So when you will take the value of u3 star and u3, both will be same, and so this term will be c square pz square over e plus mc square whole square. But you know that this u4 is what? U4 is c times px minus ipy over this much, okay? But u4 star will be c times px minus ipy. So when you will multiply the complex conjugate of u4 with u4, your result will be this. So this is c square px square plus py square over e plus mc square whole square, and that will be equal to 1. Okay. Now let us combine these two terms in the third and fourth term in this equation in LHS. So combining these two terms, you can see this result will be n square times 1 plus this much. E plus mc square whole square has been taken as a common factor, and then in numerator there will be c square px square plus py square plus pz square. But you know that this px square plus py square plus pz square is equal to p square. So our result is n square times 1 plus c square p square over e plus mc square whole square, and that is equal to 1. And so from here you can see n will be equal to 1 over this much square root. So when you will take it in the numerator, this will be n equal to 1 plus c square p square over e plus mc square whole square to the power minus half. Okay. And in fact, in the same manner, we can obtain the normalization factor for the solutions in this equation. In fact, when you will take this set of values of u1, u2, u3, again you will get the same solution. Okay. Sorry, this is for minus. For e plus, this is the second solution. So taking this solution, you will get the same normalization factor. But when you will take now these two solutions, that is u3 equal to 1, u4 equal to 0 and this much, and the another set, that is u3 equal to 1 and u4 equal to 0. In this condition, the only difference will be what? Only difference will be at the place of this e plus mc square whole square, there will be e minus mc square whole square. Only that will be the difference. So I have written it here directly that when we will use the equations in 8, n will be equal to this much. This is 1 plus c square p square over e minus mc square whole square whole to the power minus half. So these are the normalization factor. So in this way we have obtained the plane wave solution of the Dirac equation for a free particle. I hope you have enjoyed the video and understand each and every concept clearly, and so definitely you should write down these facts in your notebook, and that will be a very good notes for your examination purpose. So thank you very much.